Hello and welcome to course P28 of the Resistance Welding Process series. In this particular presentation, we're going to talk about the sequence of events through the resistance welding process and try to get to know a little bit about what we have to know for each one when it comes to development and so forth. There are 4 events that we have to concern ourselves with in this process. And in order to teach it, we have to break them down into little bits and it'll make it far more understandable. So the first one, of course, is the squeeze force and the pressure. How hard you're pushing when current gets applied is critical to this process. And making sure that the current has the right configuration of joint. That is, the pressure and the forces have closed the joint up to where it's very weldable is important to establish from the beginning and to maintain throughout the process. This is where we have trouble with stamping sometimes, where they push back a little bit. Keep in mind that squeeze is one of the ones that I think we can deal with the easiest. We can actually take resistance welding schedules, shorter schedules, and put preheat schedules in place that will actually bring the material up to so it's touching to get good contact before we initiate our welding process. There are lots of things we can do as programmers to try to compensate for these things. So next is a start current initiation and ramping. Are we going to have a ramp? Do we need a ramp? That's one of the things we have to decide, your particular situation and your material and your quality of your stamping. If it happens to be a stamping, will have an effect on these decisions. And the weld current duration. How thick is it? And how thick is it? And how long are we going to weld it for? Based on that, there are a number of factors that your choices for resistance welding caps and so forth, that those types of things will have to be a part of that as well. And of course, our cool time and our duration. How long is it going to take? How long are we going to grip onto this until we finally let go? And all of these together turn into a schedule. So let's have a look at what a typical schedule would look like. We already talked about this. We have our squeeze time. Like, how long is it going to take to meet the criteria? If you're not familiar with resistance welding at all, here's a couple of things to know. First off, we do it often pneumatically. We have special cylinders, air cylinders, that actually have oil in them. They're actually called air on oil. And the oil is in there to take the place of air so it can more quickly react to initiation. For when I'm asking for forces, I get them very quickly because I don't have all the compressible gas, air that is, inside the cylinder. So it reacts very quickly to the application of air pressure. And this speed helps with our timing cycle. Then often we have an upslope. I usually put an upslope in everything, so it makes it very easy to make initiations. Now, upslope's important to me because if there's a fit-up issue, and I've got to bring this joint in a little bit, I might ramp it up nice and slow to make sure that we hit a plastic state, because you can hit a plastic state with steel somewhere around 1600 degrees Fahrenheit, where they become pliable and they'll come together, but not necessarily weld. And I'll usually put in a bit of an upslope, and I'll increase that upslope if I think my fit's bad. Because remember that if weld metal is flying all over the place, that's a bad thing. Then, of course, we have our weld. Actually, our weld schedules are relatively easy. It's there's a million different charts out there to say this thickness to this thickness should be this temperature. But always keep in mind, when you're talking about current, it's relative to the amount of force. So if you're not pushing hard enough, you're going to get a different outcome. If you're pushing too hard, you're going to get a different outcome. All you got to do is make sure you close the joint. People say, oh, how hard do I got to push on this thing? When you're comfortable that you can't put a feeler tape inside that joint, that's when you can go ahead and hit it with a weld schedule. That's fine. But if you slip a bit of feeler tape down between that joint, when you've got it up, it's time to make sure that you put a plastic state, a pre-warm, whatever you want to call it, in there to make sure it brings the joint up. Never continue from that. Always put a little bit of a pause after the upslope, and then you can go ahead and apply your current. And of course, you could have a little bit of a downslope. I leave it there just in case. If I have HSLA, or something with a little higher carbon content, martensitic steels, boron steels, I always leave a downslope in that, because if you stretch out your downslope, you're actually starting to you're starting to anneal your joint and around it a little bit. So if I take my time cooling off, remember the slower I cool, if you watch the metallurgical side, you know that the longer it takes to cool, the softer the composition of the material will be. Fast cool, embrittles, right? But if you don't have the carbon content, if your material, again, is just a plain carbon at 1010, 1008, you could go ahead and quench that as fast as you want. You could hit it with a hose if you want. It's not going to make any difference because it doesn't have the potential. It doesn't have the metallurgy to be hardened. And then, of course, our hold time until cool. Now, making sure our pressures are hit is another challenge. As we discussed before, we have a situation where we present our material, and here comes our caps, and here comes our force. It's very important we don't start to weld before the forces are met. If I tell it I want it to weld at 600 pounds force, then I got to make sure I'm at 600 pounds force. There's going to be some math involved to know where you start on things like this. The size of your cylinder will help with your forces, and having the proper meter. I mentioned a spats before, but there is a lot less expensive meters that will just give you the tip forces. And you're going to need one to know you have the consistency. Never trust your outputs. Never trust anything, because you got a lot of mechanicals involved between one part and another. Always go and make sure you've got the right equipment to check these forces at the very least. And be very careful, because some of that equipment out there, you can't fire a current through it. So make sure you turn your welder off when you use it, or you won't be using it long. It'll burn it up. Pop a hole in it, there'll be oil everywhere. Now, the timing for these controllers, and there's usually some level of a control panel and a teach pennant, but times are either in cycles, when it's in hertz, or milliseconds, depending on what the power source is. 60 cycles or hertz is equivalent to a second, so often we're working in cycles. So, for example, 6 cycles of force, 3 cycles of upslope, 8 cycles of current, 2 cycles of downslope, and then our time for cool. So you could do it in cycles. The other option, the other opportunity here is to, if you have the right equipment, is to work in milliseconds. I like to work in milliseconds only because I can shave things a little better for cycle time, because there's about 17 milliseconds in a cycle. So I can break it down even further and start to tighten it up if I'm working in milliseconds. You find these machines are MFDC, mid-frequency DC resistance welding machines. Now, there's some complications when it comes to, if you're setting up a machine for the very first time, there's complications in setting up these tap settings. And you need to know what range, and it has to do with your duty cycle as well. There's more to setting up your tap settings than just finding a position that works. Think of it like a range. Like the ranges that you're going to set it in. And you never want to set a range to be maxed right out. And that's why they give us these tap settings, so we can figure out what range that it's going to work at, because you can't just give a person a transformer and have all the ranges be met accurately. So what they do is they give us tap settings, and it gives us an opportunity to say what gear we're in. If you're thinking about a 10-speed bike, are we in second gear or third gear? Should be in fourth gear. You know, you need to actually do some math and figure out, based on your thickness and based on your current and what you've assessed before you even start. I figure out the weld before I even look at my tap settings if I'm doing it for the very first time. I'm not worried about my tap settings until I look at the capacity of my transformer, the capacity of my welder, the capacity of and control over my force and follow through, and how all that works. Now, take note as well, often you'll find machines that do a percent heat. Remember that the percent heat is based on the maximum output of the controller itself, and usually does not include the transformer. So you need to do a little math there. If you have any questions on this stuff, you can give me a call, and you'll find my number at the back. Now, here's an example of a resistance weld schedule that was done specifically to try to get a softer effect around the welds. This would be typical of one that I would set up if I knew I was going to be welding boron steel, or hot stamped as usually called. So boron enriched materials tend to get really hard right around the weld zone. Sometimes we even weld them twice with MIG welding to do something called, we apply something called a tempering bead. The extra heat actually softens the material around it and prepares it for welding. So what we do with resistance welding is sometimes we'll run extra impulses and then adjust this cool section here. So there's some cooling phases here. And I can make these, if I make these wider, if I make them wider, I can get more of a annealing effect. If I make them much shorter, I can get a tougher effect. So my weld outcome can be drastically affected by the application of hot and cold. And we need to make sure, based on what the material we're using, that we get it right. Watch for embrittlement, especially on some of these HSLAs, SLA materials. So understanding current and force, we've been through this slide before. Maybe it makes a little more sense now as we watch our forces be applied. When we're sure that the force gets applied to where we want it to be, we initiate current. And as soon as current's done, we initiate the release, stop the current, and initiate the release. Now, like I said, it might look a little bit different if I had some HSLA or something like that in there to work on. But if I was basic mild steel stuff, this would be exactly what you'd see. I'd make sure I had the forces until the forces got to where I want them to be, initiate my current, shoot it for a specific amount of time, and shut it off. Plain and simple. Well, thank you very much for your time. I know that was quick and dirty, and there's a lot more stuff I could add. Give me a call. You have my number right here on the screen. Give me a call if you're interested in going a little bit deeper, a little bit further, and I'm sure I'll be able to help you out. Thank you very much.